Hello mathematicians, we're just going to have a quick look at volumes of solids, just to get us an overview of the topic. So we've got several methods in here, and they all, in some sense or another, rely on slices through the solid. So the first one we're going to look at is the disk method. So with the disk method, in this particular example, we're going to look at finding the volume of the solid formed by rotating this blue shape around the y-axis. So when we do that, the solid that forms is going to be a cone. So that cone there, we can imagine slicing, and because we're going around the y-axis, we're going to slice it horizontally, so that each slice will have a thickness dy. So the radius of the slice is r, and the volume of that slice is the area of the face times its thickness dy. And in the limit, if we add all the possible slices up, that integral will be the volume of the whole shape. So that will be the result of integrating from 0 to 12, the height of the cylinder, the height of the cone, the area of a particular disk, pi r squared dy, and that will become pi x squared dy. Then, when we substitute in our value for x, the value for x from our equation up the top will be 5 outside of 12 minus y all squared. We go ahead, we take out common factors, we do our integration, and we get 100 pi. And the good thing about that is that that checks out with the formula for the volume of a cone, 1/3 pi r squared h, which also gives us 100 pi. Now the washer method is simply the disk method where we have a hole in the disk. So to facilitate that in this case, I'm going to imagine rotating our slice, our triangle, around this line, the line -2. And the shape that we get then will be something like a truncated cone, and it will have a hole running through the middle, a cylinder running through the middle. So that when we take our slices are going to have a single hole in the middle, and all the slices will have a hole of the same diameter, so radius 2. So if we then follow the same logic as before, what we're trying to find are the surface areas of annular cylinders. So adding all of those sections up will give us the total volume, and we've got 0 to 12 of pi outside of big R squared minus little r squared, there should be another bracket there, dy. So big R is then the distance x given by our equation up above plus a 2, because we're rotating about the line x equals -2, minus our little radius is always going to be 2. So at that point we just go ahead and do the algebra. You probably need to really double check my algebra there, but the concept is that we do the integral, we add it up, and we get the total volume of the shape. For the shell method, then instead of taking vertical slices, we now take horizontal shells. So we take a cylinder like this, well, an annular cylinder, and that annular cylinder has a thickness given by dx, or delta x. So what we do is to, again, build up shells, so wrapping around an inner shell, and we're going to find the area of all of those shells and add those up. So again, our integral. So if we focus on just one of these shells, the volume of that annular cylinder is going to be given by 2 pi rh dx, and h is the height of our particular cylindrical shell, and r is the inner radius, and delta x is the thickness of our shell. So if we spread that shell out, then as we remember from junior school, the thickness of our shell is delta x, 2 pi x, or 2 pi times the radius, is the length of the resultant rectangle, and y is the height of the resultant rectangle. So we're going from 0 to 5, so refer back to our triangle there, of the width of the triangle by width of the rectangle, by the height of the rectangle. So 2 pi x times y. And again, x is given by this expression, x outside of 12 minus 12 on 5 times x. And y is that value of x, and x is x between 0 and 5. We go ahead and do that integral, plug numbers in, and we get 100 pi, unsurprisingly, as the answer. And our last method is again applied to the same problem, where we look at similar cross sections. Now in this case here, it's identical mathematically to the disk method, but the concept and how we get there is slightly different. So we again say that we're going to find the total volume by adding up the volumes of little horizontal slices in this case. And our horizontal slice has a radius x and a thickness delta h. And when we look at the slices, what we can see is that we're going to get that if we take the shape that if we take similar triangles, it's no longer the shape that we're rotating. So if we take similar triangles, we have this set up. So the height of a similar triangle, and I'm just taking half the possible triangle, so h over r for the big triangle and y over x for our smaller triangle. And by similar triangles, that will give us, for the small triangle at the top, the height is h minus y over h, the height for the big triangle, and that equals the base of the small triangle, x, over the base of the large triangle, r. Now in this case, we substitute the actual numbers in for height and radius, rearrange that, and we get, unsurprisingly, the same expression for x, 5 outside of 12 minus y on 12. So our integral becomes the integral from 0 to 12, from the lowest possible height to the maximum height of the area of the face, which again happens to be, in this case, a disk, so that's why our maths is the same, times the height of the slice. So exactly the same as we had for the disk. So the maths we go through and we get exactly the same answer. Now that's a very short survey, but it hopefully just gives you an overview of the pattern that we get when we go through the 4 different processes for finding volume.